welcome back to Exam Ignite YouTube channel. This is Embedded System Design Module 4 Part 2 video where we'll be discussing the second half of this Module 4, that is ARM Processor Fundamentals. So final overview of this ARM processor is, so it follows an RISC architecture as we seen, and it uses a load store architecture. So what are the features here? Data processing occurs in the register only. Then load instruction transfers the data from memory to register and store from register to memory. So this is the core data flow model, ARM core data flow model, where you have to write this as a diagram when they ask for the architecture. So here you can see we are having a sign extend and an instruction decoder, a main register file, which from R0 to R15. So the data is given to the sign extend and that is read to the register file. From there, it will go to the ALU for the ALU operation or for the barrel shifter, and then it comes to ALU. Here it's performed and the result is sent back and stored in the register, and also to the address register where the result has to be stored. If the incrementing is required, it forms a loop. Finally, this both A and the B that are from the registers are sent to the MAC. So we'll explain this. The components are, one is instruction decoder. Here decodes the instruction before execution. Registers, it store register. Barrel shifters means preprocessor operands before ALU operation. ALU performs arithmetic and logic operation. MAC means it performs multiplication operation. Address registers holds the generated memory address. Then incrementer means updates the sequential memory location. So operation is working as ARM instruction generally use two source registers, one destination register. So ALU or MAC processor operates and stores the result in the destination register. Barrel shifter pre-processes the register before entering ALU. Next is registers. These are used to store data and address. So registers are represented using the R plus number notation, that is register 4, that is R4. So from R0 to R15, these are the registers available in the user mode. So we are having three special registers, that is R13 is SP, that is stack pointer, and R14 is LR, and R15 is PC program counter. So ARM has up to 16 data registers and 2 processor state registers. Visible registers are R0 to R15. All the registers are 32-bit wide. Next, the special registers, as I said, R13 is stack pointer. It holds the address of a top of the stack, stores the stack head in the current processor mode, and register R14 is link register. It stores the return address and used during the subroutine call. Program counter, it contains address of the next instruction. Processor fetches the instruction using PC. Next comes the program status register. That is what we had here, has two status register, and CPSR and SPSR. CPSR is current program status register and SPSR is saved program status register. So next is CPSR. So CPSR, it is used to monitor the processor operation, control internal processor functions. It is dedicated 32-bit register. So this is a generic program status register, that is just a PSR. So in the CPSR, the field is divided into 4 fields, that is each of 8 bits. One for the flag field, this is status field, this is extension field, and this is control field. What happens in the flag field is it is conditional flags, like N means it is negative, and Z means it is 0 flag, C carry flag, and V means overflow flag. These are the condition flags. Control field is nothing but it contains interrupt mask bits, that is thumb state bit or processor mode information. All these are there in the control field. Then thumb state bit, that is T. It indicates the processor operating in thumb mode. Interrupt mask bit means it is used to enable the interrupt or disable the interrupt. Mode field, it is specifies the processor operating mode. So that was all about that. Next comes the processor mode. So processor mode determines the active register and access rights to CPSR. Processor mode can be privileged mode, that is full read or write access to CPSR. Non-privileged mode, only read access to CPSR. So ARM has 7 processor modes. Privileged modes are 6: abort, fast interrupt request, supervisor, system, and undefined. Non-privileged mode is only user. Now we'll go with the functions of each one. Abort mode, It is entered when failed memory access occurs. Fast interrupt used for high priority interrupts and faster action. Then interrupt request used for the normal interrupts. Supervisor mode, processor enters this mode after the reset used by the OS kernel. Then system mode, it is a special version of user mode, has full read or write access to CPSR. Undefined mode, it is entered when undefined or unsupported instructions occur. User mode, it is for the application and user programs. So the mode, their abbreviation and their privilege are given in the table. Banked register, they contain that contains 37 registers in total. So out of this, 20 registers are hidden depending on the processor mode. So they are called as a banked register. So complete ARM register set is given here. This is the user and system. Fast and interrupt requests are accessed by the interrupt request by supervisor, by undefined and the abort. So definition here is banked register, the register available only in a particular process mode. For example, in the abort mode, if there is an abort mode, only the 13, 14 and the SPSR, only these three registers are available. So like that. In the IRQ, similarly, only R13 and R14. So like that. So only these are available. Next comes the changing mode during exceptions. So exceptions cause mode change using change again the same instructions. So during this IRQ, that is interrupt request, the 13 and 14 becomes banked registers. So the 13 will store the stack pointer and 14 will store the return address. Also the CPSR is copied into SPSR. To return the user mode, CPSR is restored from SPSR. State and instruction sets. Processor state determines which instruction set is executed. ARM supports three instruction set. One is ARM, thumb, and Zyxel. Here, ARM state when t is equal to 0, processor executes. So ARM instruction features is 32-bit, high performance, and supports conditional execution. Thumb state when t is equal to 1, processor execute the thumb instruction. 16-bit processor, improved code density and small memory requirement. Next is Zazzle state. Here when t is equal to 0 and j is when processor executes this instruction. It executes the Java byte codes, then 8-bit instruction execution and speeds the Java execution. Only about 60% of the Java bytecodes are implemented in hardware. Now comes ARM versus thumb instruction set features. So this is the difference of both is given in this table. And next comes the interrupt masks. Interrupt masks are used to stop a specific interrupt request from interrupting the processor. ARM has two interrupt request level. One is interrupt request and fast interrupt request. CPSR contains two interrupt mask bits. One is I bit masks IRQ, F bit masks FIQ. When I is equal to 1, IRQ is masked, that is disabled. When F is equal to 1, FIQ is masked. Conditional flags are updated by comparison and ALU operation results. Then conditional flags, that is the flag Q is saturation, V is overflow, C is carry, Z is 0 and N is negative. And what do they do? Next is some of the conditional mnemonics are given here. You can go through that. Conditional execution is determined when the processor will execute an instruction or not. So like processor will compare the condition attribute with the conditional flag in the CPSR. If the condition matches, it will execute, or else instruction is ignored. Next is pipeline. So pipeline is a mechanism used by the RISC processor to speed up the execution. It improves the speed by fetching the next instruction while previous instructions are decoded and executed. So ARM7 three-stage pipeline is there. One is fetch, decode, and execute. Here load the instruction from the memory. Here instruction to be executed, and then finally executes the instruction and writes back to register. Pipeline instruction sequence is this. Here, for example, cycle 1, add is fetched, and in cycle 2, subtraction is fetched and add is decoded. In the cycle 3, CMP is fetched and the subtraction is decoded and add is executed. So this is called as in filling the pipeline. After filling, the processor executes one instruction per cycle. Next is ARM9 5-stage pipeline. Here we use 5 stages: fetch, then decode, execute, memory, and then write. The sixth stage is about fetch, issue, decode, execute, memory, and then write. So pipeline executing characteristics. The ARM pipeline processes an instruction only after it completely passes through the execute stage. So in the ARM 7 pipeline 3 stages, an instruction executes only when the fourth instruction is fetched. So ARM instruction sequence is given here. So here you can see the MSR instruction enables the IRQ interrupts. So IRQ becomes active only after the MSR completes the execute stage. So now the MSR clears the I bit in the CPSR and enables the IRQ interrupts. Once the add instruction enters the execute stage, IRQ interrupts are enabled. Next is program counter and pipeline. So here in the execution stage, the PC points to the address that is PC plus 8, address plus 8. Now this means the PC points the current instruction address plus 8 bits. So processor stays at the 2 instructions ahead. So here the instruction address is given like this, and then it will become adding both the addresses. In the thumb state, the PC is equal to address plus 4. Other characteristics are pipeline flush and branch prediction and interrupt during the execution are there. And the most important question that has been asked in the model question paper and June-July paper is exceptions and interrupts handling along with the vector table. So when an exception or interrupt occurs, the processor sets the PC to a specific memory address. So this address range is called as vector table. So this contains a branch to routines and link exceptions or interrupts. So the table as address of the default vector table location is 0 cross 0 0, and the optional high address location is given here. Types of vector entries we are having. First is reset vector. This is the first instruction executed after the power is on. Branches into the initialization code. Second one is undefined instruction vector, where processor cannot decode an instruction. Third one is software interrupt vector, raised when the software instruction executes, used mainly for the OS routines. Prefetch abort vector occurs when the processor tries to fetch the instruction without correct access permission, usually during the decoding stage. Next comes data abort vector. This is occurs when processor accesses the data memory without permission itself. Then interrupt request a vector, that is IRQ, used by the external hardware interrupts, like if IRQ can occur only if the I is equal to 0. Next is fast interrupt request vector, that is FIQ. It is similar to the IRQ but reserved for the faster hardware response and can occur only if F is equal to 0. And this is an interrupt vector table. You have to write this while writing the answer for this question. Next is core extensions. Here core extensions are hardware extensions placed next to the ARM core to improve the performance, manage the resource, and so on. So three hardware extensions we use here is cache and tightly coupled memory TCM, memory management, and co-processor interface. The first one is fast memory block placed between the main memory and ARM core. ARM cache types are unified cache. Here it is using the von Neumann architecture. It is unified cache. It stores the data and instruction. It is a simplified von Neumann architecture with the cache. Next is the main blocks you can observe here is ARM core, unified cache, and the logic and control AMBA bus interface unit, which is connected to the on-chip AMBA bus along with the main memory. Separate cache, here it is Harvard core, that is Harvard architecture, same for the data and instruction. Tightly coupled memory, it is TCM. Here the cache removes the performance but reduces the predictability. The real-time systems deterministic execution is important, hence ARM uses tightly coupled memory. So Harvard architecture with the TCM is given here. It contains a data TCM, instruction TCM, along with AMBA bus interface unit, logic and control with the ARM core, and that is connected to the on-chip AMBA bus with the main memory. The combination of the CAC and TCM, here they contain both of things. They have better performance and predictable real-time response. This is a simplified Harvard architecture with the CACs and TCMs. Memory management, here embedded system use multiple memory devices. Need for the memory management is organize the memory devices and protect them from the improper access. Like they have three memory management types. One is non-protected memory, one is memory protected units, and the memory management units. Next comes the co-processors. So here the co-processors is attached to the ARM processor to extend the processor features, like to extend the instruction set or to provide an configuration registers. We use more than one co-processor can be attached through the interface. They have a dedicated ARM instruction and they provide a load store type interface. Next is specialized instructions. We are having some that can extend the ARM instruction set and the pipelining operations where coprocessor instruction are processed during the decode stage of the ARM pipeline. Then comes the architecture revision where the every ARM processor implementation executes a specific instruction set architecture. Although one ISA revision may have more than one processor implementation, ARM ISA is evolved to meet the growing demand of the embedded market. So we are having ARM uses a nomenclature system to describe the processor implementation like this. This is a complete nomenclature. And the important notes that here you have to write here is TDMI feature. All the core processor after ARM7 TDMI include the TDMI features, even if the letters are not shown after then processor family, then comes the GTAG, then the embedded ICE or macro cell synthesizable version. Architecture evolution. So it has been evolved from the first ARM processor to the till date, that is an enhancement of each stages. And then comes the revision of the history. Actually it is all there in the syllabus, so I have just added a main points: ARM v1, ARM v2, ARM v2a. So these are the different ARM stages. Okay, so after this we'll move on to the processor families. Here also they are grouped into different families like ARM7, ARM9, ARM10 and ARM11 with a family attribute comparison table. So each of the ARM7 means what is the architecture. It uses one human. Then the data plus instruction on the same bus pipeline. So that is three-stage pipeline. And then ISA executes ARM v4 instruction set. So similarly, the others are also mentioned here. You can go through this table. So I think this was all about the module 4 part 2. You can pause the video and go through each of them for your reference. So that's all. Thank you for watching. Please do like, share and subscribe to Exam Ignite YouTube channel.